Nobody knows. And then I'm going to share the screen again. Good. All right. All right, so maybe let's get started. So welcome everyone. Thanks for coming. So this is meant to be, I think I'm probably talk here. This is meant to be an interactive event, but we're going to start with me sort of telling you a little bit about Julia and why I like it, I guess. And then we will have people join in to either demo or say something about what they have been doing in the community. There is a WebEx, so people are able to follow online, and yeah, and I'm recording the stream. So Julia, I guess you have all heard of it, otherwise you wouldn't be here. This is a fairly recent language, right? This was a recent piece in Nature Geoscience that sort of explains some of the reasons why people might be adopting it. There's a lot more of this sort of advocacy out there, and I won't go into that in detail. I'll just sort of, go to this. I'll do this first set of questions. And so the first one is, so why this workshop? So this workshop, I think, is timely because Julia has been really gaining momentum in the past couple of years to the point that something like Nature magazine picked it up and started advertising that it was maybe a good choice for some research scientists. And so we have also started sort of organizing a little bit of a community, this is one of the elements of it. So this is one of our Julia climate organization, where you will see that there is some tools that are being developed, and then a few people are here listed. There is a Julia Ocean also that essentially is sort of starting today. And so the timing seems right to sort of try to get people like this in the room and see how we can move forward and see if we have good reason to do that. So to the question of why would you want to use Julia as opposed to a different language, I think the answer likely depends on your preferences, and I don't want to say that everybody should use Julia. We will add to this GitHub page later on, which is here on my account for now. We will add some of the sort of advocacy pieces, but I will tell you a little bit about why I sort of went for Julia. And for me, one of the big driving factor was that I've seen a little bit of a divergence between communities. I come from doing a lot of MATLAB and Fortran myself, and for me personally, the switch to Python seemed challenging, so I sort of stayed away from doing that. But at the same time, I very much want to interact with that brilliant community that develops in Python and has all of these great tools out there. And so Julia came along, and once it reached a point that it was going to be fairly stable, it seemed like the good way for me to go. And some of the reasons for that, from my perspective, again, this is just my personal opinion. So the fact that Julia uses the same Jupyter interface that say Python, R, and all those other languages, for me was a big factor. I see it as a bridge between different languages, and I see it also as a bridge between communities, basically. It's an easy switch from MATLAB, I would argue, but Python is also very much fine. R is also great. Anybody going for those languages would be very, very smart to do so. And so I really don't see this as a matter of opposing one language to another. In fact, very much the opposite. The way that I see it is there's GitHub and all of the technologies that have developed around it, all of the cloud stuff. That was, for example, advertised yesterday in the Pangeo tutorial. By using Julia, you benefit from all of that, and you have this common platform in the Jupyter interface that connects you to those other communities. And then there is native support for coding, say, Python libraries. So I do, in fact, rely on a lot, or frequently on a few, let's say, Python libraries, such as for plotting, there's this PyPlot and CartoPy that to use. I also use APIs that call, say, data servers that are the front end being written in Python, sorry, and so on and so forth. So these were some of the big motivations for me. And then, of course, the language itself is appealing to me. It's appealing to me for various reasons, but one of them is especially that it is a compiled language. You don't see the compilation happening in front of you. You don't type make, but it is a compiled language, so it is potentially very fast. And in fact, once you start coding in Julia, fairly easily you get to something that's pretty fast. Yes. Oh, is this thing on? Sorry. Oh yeah. Is it? No. Let's see. Can I try to speak louder? Because I don't think that this is live. Sorry for that. No. So I'll speak louder. 1 second. Right. So Julia is a compiled language. And so what that means is that it goes fast to the extent that you follow a certain set of principles which are not very complicated. And it becomes really fast if you know what you're doing, which is not really my case, I guess. It is also a very mathematically formulated language, which is something that I really like. And so in my opinion, within reach is a scenario where we can have us using, for the bulk of our activity, or for those who choose that, just one language instead of two, right? So instead of having MATLAB and Fortran, for example, or Python and Fortran, or Python and C, you could imagine really working in Julia, solely in Julia. And I would argue that because of some of the way that it's designed and the way it looks, it's really a language that potentially could, bridge from like a 10-year-old person to like a 90-year-old. And I don't think we're far from that. All right, so I probably have said enough about this. I've already mentioned a couple of the important Julia features. There is a couple other ones that are worth mentioning as we go. So the just-in-time compiling is what makes all of the magic happen in a way, right? So you type a command, the first time that you call that command, essentially it gets compiled, and the second time it goes super fast. Another feature that I really like is this so-called multiple dispatch. And so compared to, say, Something like Python, it feels slightly different. There's a type system that allows you to specialize your methods to different types. And so you end up with code that is really reusable, where you write something without the specification of any sort of tie to a type. So you can write A plus B, right, and have A and B be a lot of different things, and it's always going to be the same code. Is there one that should be mentioned? Another certain feature that should be mentioned? I'll move on. No? All right. So then we're going to talk a little bit about where we are, right? There's a lot that's been done already. There is, since August 2018, there is a stability to the core features of the language that came from the release of this so-called 1.0 version. So that is at that point that people started really investing more time and effort into that. And so that's when some of the bigger projects, like say the Klima project that you may have heard of, decided to go with Julia. Since then, a lot of tools have been consolidated. And so at this point, there is a good set of libraries for plotting, for example. There is those that are listed here. So 3 of them. This one is probably the less mature one in a sense. It's mature, but it's still in very active development. This plots library is sort of the default, and so I'll show you an example of that. And then this pipeline is the interface to the Python libraries. And so when you want to do something like that, integrate with Python, you have this PyCall function that you're going to build. You're going to have your dependencies, right? But then it's going to be pretty straightforward, just coding it from within. I don't know if they have a plot here. They don't. I'll go to my stuff. So this is an example that was done with the plots.gl package, right? And this is an overturning stream function, as you might recognize it. I think I have a couple more things here for you. This is an example with the so-called Makey. And so this is my little Lagrangian tracking that I'll tell you a little bit more about later if I have time. And then in this same package, in fact, there is right. So this is what you do with PyPlot, for example, right? So this is based on PyPlot and Cartopy. So plotting is pretty much covered. The whole set of packages that allow you to read various types of files and write them is also quite mature at this point. So for netcdf, for example, there is this netcdf.gl. There's another one that I think Alex will tell us a bit more later about. So maybe I'll skip that. This is something that we've been writing as a way to sort of do distributed netcdf IO. ZAR is this up-and-coming approach to integrating with cloud data. CSV is just when you're going to read a basic text file. I think everything's okay there, but the microphone doesn't work now. Aha. Okay. So as you see, I'm very not technologically fluent. So the fact that I'm able to use Julia should tell you something. What time is it? Okay. Right. So then we have also libraries that are there and pretty well developed at this point to do data analysis. So this data frames, for example, is something that's very very similar to what the community in Python uses for tabular data. This climate tools is one of our under development set of tools to do analysis of climate model output, for example. This ESDL.gl is something that colleagues at in the Earth System DataCube.net are developing, and I'm going to ask whether Megart is here. Let me see. Okay. All right. Is somebody available to talk online about ESDL.gl? Maybe not. All right, we'll come back to it. All right. Yeah, so this is a package that I haven't actually used myself yet, but it looks very, very promising. So here, then I listed a few things that, and this is a subset of what's out there. A few things that maybe you want to take a look at that really relate to somewhat what we've been doing in the past. So this Global Ocean Notebooks folder of mine is where I have examples that have to do with the computing this sort of quantities from a model output. There is something here that does the so-called Helmholtz decomposition. If you've come across this paper that I published last year about ocean heat transport, and that's basically what it is. This is how you get to an overturning stream function. And this one is this Lagrangian tool that I've been developing, which, to give you an order of magnitude, basically comes to setting up a problem, calling the ODE solver package, which is great. That's one of the real strengths of Julia at this point. And then you get about, for example, 50,000 particles computed within a minute over 20 years. It takes longer to plot the thing for me than to actually compute the trajectories. And then in there's also a few things that you can look at about those data types and so on, NetCDF here. So you can try all of these with Binder, right? That's one of the beauty of GitHub. That allows you to plug that. And so in those cases that I've shown, I'm using this Mesharis package, which is a representation of arrays and the support for the Sigrid in Julia. Individual displacements is what does the Lagrangian part, and this is something I started to look at or transfer my pipelines that rely on Argo data, either directly or via an API. This is a bit of it's a simple concept, but it's a way to drive or to launch say the MHGCM, for example, from within Julia, and to distribute tasks. So that's another aspect that's very well developed and very useful, is there is support for parallel computations in Julia that is very good. You can have GPUs and so on. Then I'm going to ask Benoit to come and talk about his stuff a bit, and then we will have Alex tell you about his. So Alex is in Belgium right now. Don't walk on the cable.
Thank you for being there. It's amazing to see so much interest for Julia. I'll be really quick. I do global marine biogeochemistry modeling. So I made a package called IBEX. Click on it. Very quickly show what it looks like. And it makes it really easy to explore your ideas and your concepts. This is like documentation, and there's tutorials. And just showing one example in like 20 lines of code in a Jupyter notebook that you can run with Binder as well. You can plot the ideal mean age in a global 3D model in 30 seconds on a 10-year-old laptop. So that's pretty cool. And I do a few other things. Where's the main page? This one? The first one. I need to deal with data from the World Ocean Atlas, from geotraces, so I make packages for those. I need to have types for ocean cruise data. I also worked a little bit on something that I think is really interesting, It's Julia has a very nice package for dealing with units called Unitful. So you don't have to worry about all these conversion mistakes that you make all the time, and it takes 5 days to figure out what was the conversion error. And I helped write a package for plotting things with units. I'll do just that, and then I'll let the next speaker talk. And we'll have some documentation and examples. Simple example. Say here, take a random something with kilograms, and the plotting thing realizes, oh, that's kilograms, and it puts it on the axis. All right, it can be useful. Stop there.
Awesome. Well, I'm going to take this opportunity to emphasize this beautiful documentation framework that they have, right? This is quite practical to use. It's built in, and it comes also in association with the package manager, which has really benefited from the previous experience of, say, Python and all of that. And so the package manager in Julia is one thing that I really, really like. So there's probably in your documentation somewhere, and maybe not, but I'll go to here. I'll do that here. Nope. All right, whatever. All right, so this is the package manager in Julia, and again, with a nice documentation. And the way that this works is, you have this mode that's package management. You do add example. It's an example of a package, right? Now that is installed, and then you go back to your normal mode, and you can just do using that package, which is somewhere down the line. So it's very kind of well put together, and I was just meant to say that. Alexandre, do you want to take it on? Oh.
Yeah, hello, can you hear me?
Yes.
Yeah. Great, I will share my screen.
Yes, let me stop.
Select window. Okay. Do you see my screen?
Yes. I'll make that bigger.
Great. So here I have a presentation of the some of the package that we're developing at the University of Liège in Belgium. So one of our main packages is called DIVA ND. So that's a package to create gridded climatologies from in situ observations. So you have a collection of temperature or salinity profile data, and you want to have a grid climatology. That's where you can use DIVA for. So essentially, it tries to make a continuous field, a smooth field, which is close to observation. And so formally, it minimizes the cost function. So it's a bit similar to spline interpolation. And it can take into account things like the topography and ocean currents in this interpolation process. And it's a bit similar to optimal interpolation that some of you might know. And it can provide consistent error variance estimation. Originally, DIVA is a quite old tool. It was written, I think, more than 30 years ago, originally in Fortran, and we have now ported it progressively to Julia, in fact, since 2 years. So, and we use it in several of European projects, and we have also making regularly DIVA workshops. And for this, for instance, we have some notebooks on this link here that you might find interesting if you want to apply DIVA. There's some other package that we are working that we have developed. So we created a package to manipulate and read netcdf files. So we tried it to make it quite convenient to use. So it applies directly some netcdf CF conventions, and it can support the CF calendars, and it also support for some more advanced features like compression and variable length arrays and netcdf groups. And if you have sometimes you have data files aggregated by day, so you have maybe one data file per day, and you have 365 of them for a full year. So it makes sense to aggregate them over a dimension. And so this is also supported by these NC datasets. There's another package for manipulating netcdf files. It's called netcdf from Fabian Ganz. This package supports more MATLAB and Octave-like interface, while NC datasets more like a Python-like interface. Another package that we have developed is called PhysOcean, so for physical oceanography. So one of the things that you need to compute quite often as a physical oceanographer is computing density or computing the Brunt-Weiseler frequency based on temperature, salinity, and pressure. So that's the equation of state 4. And so there is the old version, this called EOS80, which we have implemented in pure Julia. There's also some functions to compute heat fluxes between air and the ocean, geostrophy, steric height. And we also integrated into this package some functions to grab automatically in situ data, either from CMEMS, the Copernicus Marine Environment Monitoring System in Europe, or the World Ocean Database in the US. And we are also collaborating on working on the TEOS10 package. That's a GIP seawater. That's a new version of the equation of state since 2010. That's one of the new recommended way to do it. And finally, we have also a package which is called Data Assim or Data Assimilation. So we use this package to teach students about data assimilation methods. So we implemented several data assimilation methods in this package. I put it just the most common one in bold here, like the ensemble Kalman filter, ensemble transform Kalman filter, and the local variant of these, and also incremental 4D var. So these are our main package that we have developed at the University of Liège. And this slide is here online at this location, and all the titles are actually the link to the GitHub repository. So if you're interested in, have a look to the GitHub repository.
Great.
Okay, thanks. That's what I wanted to say about our packages.
This is great. The links are also on the repository for the workshop, actually.
Exactly.
Yeah, and I have to say, Alex, that I mean your packages are great and very, very useful to us. We love them. Thank you for that.
Oh, thank you. Nice to hear.
All right. Oops. I think you need to. What am I doing?
I stop sharing.
Oh yeah. There you go. Thank you. Do you mind going back on mute? Thanks. Oh, I see. All right. Okay. So now, so we sort of covered two sort of groups, if you like, of packages and functionalities that have to do with sort of the basic sort of things you like to do, reading files and plotting stuff. Also, somewhat more advanced analysis of both data and models in Julia. And now I'm going to ask Milan to talk a little bit about his shallow waters package, which is going to be our first example of models written, in fact, in pure Julia. So I will release the screen and ask Milan to take it. Can you hear me, Milan?
Hey, everyone. I think I just share my screen now. Yep. And does that work? Can you see my slide?
Yes. Yes, we do. I'll put it on the bigger screen.
Yeah. Okay. Yeah, so I just want to introduce you very quickly to shallowwaters.jl, which is a Julia-written shallow water model, compared to what you will probably see in a minute, Oceananigans. That is, yes, it's a fairly easy, like a toy model. However, and it was really written with a focus for 16-bit numbers. So, I mean, probably you know that there are quite some efforts to write models in single precision, so 32-bit, and most people say like 16-bit actually cannot really be used. And basically, I've written this model to prove that actually we can also use 16-bit numbers. So the picture that you can see here in the middle is actually trace advection simulated with 16 bits. So like the whole model can be run with 16-bit. And this is really where things are different from like Fortran, because with Julia you can have a fairly convenient interface to also new architecture like GPUs or TPUs. Although I haven't done this here, this is more like an information theory approach of really investigating whether you can use something like 16-bit. But obviously, you're also welcome to use that with 64 or 32-bit numbers. So the model is actually not faster, but I'm basically investigating how much you could use 16-bit numbers. And then just here, if you add shallow waters, if you just type in Julia using shallow waters, then you just have this run model function, and you can basically very easily just specify all the parameters that you want. And as with most Julia functions, one of the first argument here is just the number format, and you can basically plug in a lot of different ones. And you can, I've been developing a couple of different number formats, and you can just like plug and play them in, and it runs on the same code basis. It currently uses netcdf as output, and I will also implement some MPI parallelization soon, so to actually see how much can we reduce the communication if you parallelize things. So in a couple of tests, I've already seen that I can reduce the communication down to 8-bit, and how you can actually do this in Julia will be one of the future projects. Thank you.
Great. Thank you, Milan. Do you mind releasing the screen?
Yeah.
Thank you. And I'd like to emphasize this something that Milan said, which is, in this case, you just change one string, which defines your type, and your model just runs completely on a different type, which I think is pretty amazing. All right, I will take the screen back here, and oops, no, not this way. And then Greg is going to come and tell us about Oceanography that he develops with Ali Ramadan.
Hello, everyone. So Oceanography is a finite. Okay. So let me get to the GitHub. Works. Is that all right?
Yeah. Looks good.
So this is Oceanography. It's being developed as part of the Klima project, which is a project to write a new Earth system model all in Julia. It's being led at Caltech, MIT, Naval Postgraduate School, and JPL. So the Klima model is its own thing. It's based on a discontinuous Galerkin numerical method, and there's an ocean component, an atmospheric component, a land component. Oceanography is sort of like a side project within the Klima organization, and it's a different model that's based on a finite volume numerical method. And so it's a code that solves Navier-Stokes equations, basically, for the purpose of large eddy simulations, so practical simulations of ocean turbulence. We focused so far on small-scale turbulence problems, but we hope to be able to run, larger-scale problems, sub-mesoscale, mesoscale, etc. So I'll just briefly show you a movie. So I guess I'll just say right now, Oceanography, if you do research with Oceanography, you're going to be using GPUs. We hope eventually to have CPU parallelism and GPU parallelism so you can run large models. But right now it's your laptop or a GPU is how you run Oceanography. And just to show you an example, we have, so this is, my co-developer, Ali Ramadan, likes crazy color bars. So just bear with that. But this is a three-dimensional simulation in which there's an initial stratification, density stratification, and then we cool it at the surface, which leads to convection. And I think this is without a large LES model, but for practical problems, we typically use an LES model. So on a GPU, you can afford about 384 cubed points, or 512 squared by 256. So that's about the largest model you can run currently with Oceanography, which is enough to do research. And I'll just say, so to the point of, this is not just about models, but about Julia, so I'll just show you some code. So let's look at, oh wait, actually, let's go through the documentation. So an example, this is an interesting one. So to set up a model, there's some syntax, okay? That's not super important. But what I just wanted to highlight here is that, so this is when we build this type that defines a model, allocates all the memory and stuff. If we want to run it on so this would run on a laptop. If we want to run it on a GPU, we add a line here, architecture equals GPU. And then the same code that you wrote just runs on the GPU. So that kind of abstraction is what enabled by Julia, and that's kind of the amazing thing about writing a model in Julia. I guess, oh yeah, we also, you can set initial conditions with functions. You have this nice syntax for defining a function, which, what is a function? Dictionary will tell you if you need to know. And so, you can run, so, and we allow arbitrary tracers. PhysOcean is interesting because now we can probably use that to have any equation of state. And so right now in this, I have a buoyancy tracer, a plankton tracer, and when the model runs, it convex at the surface, and the plankton wants to grow at the surface, but then it also gets mixed, so interesting stuff happens because of that. Okay, see you on GitHub.
Yes, a lot of that is on GitHub.
Questions?
I prefer two, but I mean, you can do one.
Yeah, I was just going to say, is it inherent part of Julia that anything that's unique to this model?
So what Julia enables is there's a package that's being developed by our collaborators that allows us to write kernels. So the functions that calculate derivatives and like the right-hand side of the Navier-Stokes equations, we can write those functions such that they can be evaluated on the CPU or the GPU.
Okay.
So that's what Julia enables. But it's not out of the box, right? So Julia is actually a very small, it's just the syntax and the infrastructure when you download it. When you really use Julia, you use all of the packages that are part of the ecosystem. So the answer is there's a package for that. And so if you use the package, you can do it.
Okay.
Yeah.
And you can always contribute to any package too. I think Navid is next. Oh, you want to do it? Okay, cool.
All right, I'm back here.
Yeah.
So in a past life, before Oceananigans and Klima, well, no, I still work on this code a lot, but Navid actually probably is contributing more work recently. We developed a package it's actually an organization called Fourier Flows, which is it's a very simple package actually that just helps you develop codes that use pseudospectral methods to solve partial differential equations. So that might be turbulence problems. Simple turbulence problems in tracer, transport, etc. One of the sub packages is Geophysical Flows, where we have models for two-dimensional turbulence. We have a barotropic quasi-geostrophic model, multi-layer quasi-geostrophic model, where Navid actually. So does it run on the GPU yet? Yeah. Okay. So we've developed a similar abstraction as Oceananigans, partially maybe leveraging some of the experiences that I had with Oceananigans, so that we can run these models on CPUs or GPUs. And I guess And so, should I show? What else should I show? Maybe we do lots. Do we have?
Go to
Oh.
In the organization.
Yeah. Rossby wave dispersion. So this is an example, I guess, using the barotropic QG model that sets up a Rossby wave, if you know what that is. Obviously, you can tell I'm a physicist, so I don't know how many of you are physicists, probably some, anyways. But we've developed a similar it's sort of reminiscent of Oceanography, although but not exactly the same, where we idealize problems or models as Julia types, and we initialize them with keyword constructors, and then we run them. And so this one runs
If you run it, you will see it propagate.
yeah, which I'm not doing, but
Great.
yeah, all right.
Thank you. All right. Well, I'm just going back to. There we go. Okay. Right. So you've seen a little bit of code. You've seen the fact that it's all built into this this Jupyter interface, right? In case those things are not familiar to you, I've added a couple links in here that go back to stuff we did. So this is just the GitHub Guides. If you have never used GitHub, it's very straightforward, and you'll like it. It's a version control system. As most of you know, it's also a social network, right? So for example, if you go, well, it very much is. If you go in the repo for this, for example, you will see. Yes, that is true. The star package, yeah. So you can put stars on the packages, but you also have discussion threads, right? So for example, the discussion having to do with this particular repository that you're looking at here, you will see that everything happened between yesterday and today, and you see people discussing, and all of that is archived, and so this is something that, in my mind, is also very, very useful. That you don't benefit as much when you do MATLAB, but if you do Python, you're used to this. And so there's a couple links in there to. Oops, I went too far. That points you to the GitHub Guide, and there's this this thing that we did during IAP at MIT. So that's the period where there is no classes, where we have this was led by Henry Drake, and I provided my little contribution to this, where you'll find various things that we sort of designed a bit as a boot camp for new grad students. And so in this number 3 here, you'll find a bunch of explanations about GitHub and all that.
This is holiday.
Yeah. Well, that's the only time of the year we actually do work. Anyway, so I'll leave it to that. I think the next 20 minutes or so, we can do a Q&A. And I will just, before we go there, because I probably won't have time to come back to this, I'll mention a couple of things. So this repository is going to be there for the long run, right? You can go back to it. You can participate in it. If there is things that you would like to advertise in it, please do that. There is one thread for questions. I think we will, hopefully answer a couple of questions between now and the end of this workshop. But whatever you want answered, you can always go here, right? And you go in there, for example, and you post your question, and then you can keep that discussion going further in the future. That is this bit. A quick word about GitHub organizations and contributors. So on GitHub, you can have your own account, right? You can also join in with different organizations, and that's there are organizations that are tied to a project like Klima, that are tied to a lab, like the one that we saw in Belgium earlier. We have a couple of organizations that we're sort of setting up right now, and that are meant to really be like community, or at least that's my intention with it, to be like community sort of default places for any contributions you might like, that may be independent of a particular source of funding, lab, or project. And those are Julia Climate and Julia Ocean. So you can again go to GitHub and that. Right, so this is the Julia Ocean one. Right now, there is essentially Benoit and myself that are just so that you know who to blame. And then we're going to have a discussion about how to do this. I know the spirit is to do this, even the design of those things on a community basis where anybody can pitch in. And so feel free to come, ask questions, complain, make suggestions, etc. And so at this point, I will open it to the floor. I would ask if you can to keep the questions and the answers relatively short. But so thank you for your attention so far. And are there any questions? Thank you. Yeah.
So I would like to write. Is it possible to have that code, that function exported and put into all that function?
So I don't have much experience with that. I'm pretty convinced that from Python it's a non-issue. From within MATLAB, I have not tried, but I think there's also support for that. Has anybody tried? Right.
No, it's not very. I don't think you can.
Yes.
That, but you can't go the other way. That would require MATLAB.
No, but in the reverse direction, so Julia, can take R, Fortran, C, Python, whatever, essentially. So it's a good place to be. More questions? Yes.
Have there been tests comparing physics code scaling up to thousands of processors?
Yes, they have, but so maybe somebody has experience with that here? Right.
I think, so I don't. Almost all.
I guess more generally, there have been a lot of sort of proof for different kinds of operations and subsets that you can get to the speed of C or Fortran. My small bit of experience is I run these Lagrangian particles in Fortran with the MHGCM. I run them in Julia, and I think the speed seems somewhat comparable. I have not made that precise. Well, okay, so MHGCN is apparently slower than Oceanography, but it does a lot more stuff.
So how do you
Have to. There's a technical answer. There's one part of the code that. Yeah, we could. Already. But one of the professor tools. That package will be. Then we'll have.
All right. For those who are online, we were talking about performance, and then we'll take another question. Okay. Yeah, I think there's a, so maybe about if I can sort of open or redirect the discussion a little bit with the data analysis type of things, or the kind of functionalities that people might want, or that for them really matter.
Yeah, so my question is, I use Xarray and Python a whole lot.
Yeah,
and it seems like
Xarray.
some of that functionality is going into the NetCDF. So how sort of aware is your NetCDF and Julia of dimensions? Or Dask? Yeah, Dask as well.
So the question was about Dask and Xarray. Maybe somebody online wants to pick that up. Right? Yes. So I mean, I would say that there's a lot of those functionalities that are there. That so this ESDL.jl package, for example, is sort of, I think, the closest to a full-featured version of Xarray, if you like. My sense is, in general, I really like modularity, and there's support for parallel task submissions and all of that stuff. That's one piece of it. You have a bunch of different schedulers. You can do lazy reading from NetCDF file. That's not an issue. We have different array packages that allow you to sort of combine all of those things together in some way. I think there's also a project that's under the Julia Climate organization that's called Climate Tools, which is also related to this in a sense. So I think it's an emerging solution, but it's close. Anything else? Yeah.
I would just say there's several.
Yeah.
So I think that's important.
Yeah. Then, yeah, I would guess to summarize for those who didn't hear online that there's several branches of development in that direction, I guess. Yes, and if you forget, please use the issue tracker to ask us again, right? That's sort of the way it's there. I guess one thing I would highlight also is there's a lot of machine learning libraries out there in Julia that are very mature, and the ODE stuff is great. There was another question there. Okay, I guess this is a question for Milan, just about the shallow weather equation package. Sorry, the shallow weather.gl package. The question was whether you can use, I guess, variable topography and how much generality you're aiming for.
So I personally was more looking into the actual numerics, so like what kind of numbers are actually propagating through the model and how can you squeeze these numbers into 16-bit. The model does support topography. Currently, you have to basically like write your own function of like, this is how my topography looks like, but yes, you can. So like the model, the picture that I've shown has a ridge in the middle, like a Gaussian bump, basically. But yeah, you can. There shouldn't be any problem. And if you want to have any improvements, just raise an issue on GitHub, and I'm happy to implement whatever is needed.
Yeah, it's always, when there's a feature that you'd like to add, you're more than welcome to suggest it and even jump in and help. But the composability to me is a very important aspect, in fact. So one thing that we haven't done yet, but I think it's not far in the distance, is we could take, Milan's shallow weather equation, right? Run particle tracking on it, right? And then put Oceanography in each of the particles and run a non-hydrostatic simulation that way. That should be fairly straightforward and kind of, fun. Other question? So the question was about, is there a type that sort of corresponds to MATLAB types? And so there is in fact a mat.jl package that you can read your .mat files in it, and it's going to map that into Julia memory.
I think that it's not disruptive.
Okay, yeah.
There's a dictionary.
Right.
But you can also define custom types. They're actually called structs.
Yeah. Yeah, no, the type system in Julia is a real strength. I would say it's right. Everything has a super type, and so you have a real kind of logic to the type structure, and that's very, very useful for debugging, for example. Yeah, another question?
Add on to that.
Yeah, the point was we can extend types and benefit from the performance. Yeah, so that's an example of defining a struct, a type, which is my little GCM array type. And so what this is basically an array of two-dimensional arrays, right? And then you can have operations on that, like say size, right? That detect that this is in fact for this type, right? And so it's the same code that you just write in general size of something. And as soon as you defined it for your type, then you can do that. And so all of the stuff that's in this block here, this is the exact same commands that you would write for a regular array, right? Except now multiple dispatch figures out which methods to use, and it goes with like the most restrictive method that applies essentially. And then on top of that, there is this feature called broadcasting, which comes to just writing a dot, right? So that is you're going to multiply two arrays element-wise, right? And because it's been specialized for this new custom type that I defined, that's the exact same command you would do with an array. So the reusability of code is actually very nice in Julia. Is there another question? All right. Yes. Yes. I'm putting an example of how you call it. In fact, that's what I use in the. So this is my Lagrangian particle tracking thing, right? And so everything up to this point is basically just defining the problem. Well, I guess there's a bit of extra code in there. This one line here, that's coding the ODE solver, and that's what does the whole computation. And you can, specify a bunch of different. I guess this defines it and this solves it, but you have a lot of different numerical methods that are defined in this differential equations.jl package, which has, in fact, a lot of sub-packages. Is an awesome tool, and you can do a lot with that. So yeah, good point. Other question?
Those about the speed of benchmarks where they have sort of written way and compare it with the normal. But of course, if you really want to fast in Python, for instance, of course you vectorize it. And then you know if there's been any best practice Python things.
So I don't have necessarily a full answer to that, but I guess the question was, how does well-written Python code compile in some way, compete with Julia code? I imagine in some cases, that might be equivalent, and I don't think. I think one of the nice things about the performance in Julia is it comes very naturally. Right? For example, vectorizing, you can forget about that. There's no need for that. You just write a loop, and that goes fast by default. And then, if you put a bit of effort and you do a few different things, I mean, there's a lot of examples where you beat C, right? So I don't know how often I've seen pure Python beat C, but I have seen Julia does that. So, I mean, I don't really see it as a competition in many ways personally. In fact, I see it as the opposite, as a bridge, like I said. So, my discussions with my Python friends have become a lot nicer and chill since I've started using Julia instead of MATLAB, for example. And so I think it's an important thing. That's one of the motivations for this workshop, is to have people in the room and sort of community build like that. And so this is I'm very glad that as a Python programmer, I suppose, that you're here and having this conversation. So thank you.
I've used Julia all the time. Switching first person. That's doing. Me at least, that I can find it.
Yeah, no, I mean, and there is a large community that benefits a lot and loves Python, and I'm very supportive of that in many ways. I think it's great. I would tell you, for example, that I use more Python now than I used in the past, and that's true, Julia. Also, when Conda came up, that helped me. Yeah, I've had this conversation with several people, and I think Python, especially as a first language, is a great one because it's simple and it's very good, and there's all sorts of great stuff done with it. I think Python, R, Julia, MATLAB, in fact, are all great frameworks, and they will live together for a while, and then maybe there'll be another one. We'll find out.
For users, especially if you're only allows you to develop hyperform. I think that's the old point that you go to Europe and switch your language to French.
Yeah, Greg's making the great point that we all, in essence, use a lot of different languages, right? And there is no opposition between the different ones, I think. One last.
All that one thing. For seamless Python.
Yeah, no, so the comment was that it's very easy to call Python from Julia. And in fact, so yesterday I was at this AirDAP and at this Pangeo, right? And it took me an hour to get that running in Julia. just by calling the API, right, without recording anything. I think I'm very happy with that. So maybe we've finished the allocated time, so I will thank everybody, and especially the people online also that contributed and took out of their time to advertise. Thank you, guys. Thank you.